Let's start from the beginning with some basic definitions. Energy is the capacity to move matter. We usually use joules or kilojoules for it. Kinetic energy, you know, is the energy of motion. And potential energy is the energy of position within a force field. And a lot of times, especially like in physics, you're talking about position as far as being up off the ground. That has potential energy based on the force field of gravity. So these two, I'm going to differentiate these from the energy of chemicals by calling these bulk energies. So when I talk about these being bulk energy, in the lab, that kinetic energy would be a large object falling. I'm not talking about the energy of the molecules bouncing around. I'm talking about something falling on the ground, something being thrown across the room, that type of bulk energy, large scale. And hopefully we don't have a whole lot of that happening in the chemistry lab. Potential energy in the lab, we're talking about something being up off the ground. Okay. We're going to largely ignore these when we talk about thermochemistry because those are pretty constant. When you're working in the lab, hopefully your beaker is remaining on its hot plate. It's not flying around the room or dropping on the floor. We're interested in the energy that is within the substances, in the atoms and molecules. The internal energy. So we use a capital U for that. It is the energy of the molecules and atoms. So it's not the beaker flying across the room. It's all of the little vibrations and attractions within the molecules at the molecular level. So not the bulk, the atomic level energies. So the total energy of a substance depends on these bulk energies, but also on the energy at the atomic level. So this internal energy, again, atomic level, we're going to ignore changes in position and bulk velocities. Heat, as you know, is energy that flows due to a temperature difference. It is the movement of thermal energy or transfer of thermal energy. Energy is constant, conserved for the universe. We say these grand words like the universe in thermochemistry or in thermodynamics. That's just to say overall. Energy is also conserved in a closed system. So we need to talk about what that means. A system is just an imaginary division so that you can talk about or do calculations on a certain part of the universe. In other words, in this case, I've used this dotted line to make a system. I've defined my system as my hot object only. And then I can talk about the system is losing heat. And this out here would then be the surroundings. The surroundings are gaining heat. So surroundings are everything outside the system. And it gives me anyway, system and surroundings give me a good way to talk about that and also do calculations. Now this system is an open system because there is something crossing the boundary. We have heat crossing the boundary, so then it's considered open. A closed system has nothing crossing the boundary. Here we've taken the same situation and we've drawn our boundary differently so that we can say this is a closed system. The insulation helps us create a closed system. That way we know that all the heat that is lost by the metal is gained by the water.